Great. Hello, everyone. Today we have the pleasure of hosting Yuki Asano. Yuki is leading the Fundamental AI Lab, in short, FunAI Lab, at the University of Technology Nuremberg as a full professor. He was an assistant professor earlier at the University of Amsterdam, where he collaborated with Qualcomm AI Research. Yuki received his PhD from Oxford VGG, where he worked with Andrea Vedaldi and Christian Rupprecht. His research interests include computer vision and machine learning, particularly self-supervised and multimodal learning. We are very happy to have you, Yuki. Stage is yours.
All right. Well, thanks for the introduction and thanks again for the invite. Yeah, next time in person. I've been to Istanbul once so far and it's been very nice. Also, you forgot to mention PhD in VGG, supervised by Andrea and Christian, and went to lunch with Fatma.
That
So
was
yeah.
my contribution to your PhD.
Yeah, exactly. Yes. So yeah, all right. Let's get started. So I did a bit of digging. So this thing, X is dead, long live X, is actually a really old saying coming from like 1422 after French king died, Charles the Seventh. So yeah, it's a really long saying and basically saying that, okay, something is dead, but it will continue to live. So I guess that's already slightly the spoiler for the talk, but let's see. All right, so first of all, a bit about self-supervised learning. So I don't know how familiar everyone is with self-supervised learning. Probably heard of it, probably know the gist. I thought I'll still give a high-level overview. All right, so self-supervised learning, let's take a look at it. I would view self-supervised learning as the following alongside this picture. So you have something where you have a forward movement, which is that the model improves towards some desirable property. So we care about learning neural networks and how this model is guided. So kind of the leash, and that's the data. So it's not guided by any human annotations, but just by the pure data on its own. And sort of how we or where this model is going, or sort of the motivation, that's what we typically call pretext task. So anything really that gives us gradients. This could be all kinds of things, and we'll go into them in a bit. This pretext task, as I mentioned, is usually not the final use case of the model. There's some sort of exceptions to this. And it's constructed without any annotations, typically using only augmentations, some modifications, masking, etc. Examples include, of course, clustering, masked image reconstruction, contrastive learning, cross-view embedding prediction, and of course in NLP, this is masked token prediction. One second. All right. All right. So yeah, a bit of the story of how I came to SSL. So when I started my PhD, there were these works already in SSL, like RodNet, Deep Cluster, and then eventually also non-parametric instance discrimination from Berkeley. And it was a beautiful field, like nothing particularly happened there. And so then we went there and made basically Deep Cluster, state-of-the-art method, a bit better, got state-of-the-art, worked really well. And then immediately, I think 2 days afterwards, 𝐂𝐤 published the �ྨ𝐿 paper, which trained, I think, 4 times longer than we did back in the day. And eventually got SOTA, of course. And then, of course, Geoffrey Hinton with SimClear and then BYOL. And then eventually the whole field got really, really crazy. And then Dino V2 came out, and then people took some of these principles to multimodal learning with CLIP and SIGLIP, and sort of the end of history in a way. Before I go into more of this talk, maybe just a brief sort of background of why maybe you should listen to me about some things about self-supervised learning. So this was this work Seller that I just mentioned, this synchron-based clustering method. This eventually is sort of the lineage of what happened afterwards. And I guess like this is just an overview, maybe mostly for myself. But what you can kind of see here in the middle upper half is Dino and Dino V2. And so Dino and Dino V2 both are clustering works. I mean, they call themselves sort of distillation-based methods, right? But if you look at the laws, if you look at what's happening, it's all clustering-based laws, and especially starting from Dino V2 and V3 again, they all use this Synchron-Knopp-based optimal transport clustering laws. And so yeah, this is sort of the whole lineage, and we've developed these works further for dense clustering, for learning from single videos, or combining these with point trackers and all sorts of things. I think the main domain or main ideas we've had is combining in the stream, combining this with videos and trying to make some sense of how we can learn from videos. So that's happened there, of course. But meanwhile, of course, the elephant in the room clip model and all of these other big models that came out, VO, Qwen Image Edit, all of these really, really amazing models. So of course, 𝐒𝐸𝐭 as well. The question is, which path would you now take? If you just look for CVPR, X in the title, where X is either self-supervised or vision language, it looks like this. Sort of one spoiler is, of course, like if you typed in something like Adam, maybe it looks similar because no one bothers to cite or use Adam anywhere anymore. It's just standard optimizer, right? At least maybe you describe it in the appendix or maybe just in the GitHub repo. But before we talk about which path to take or if this is even a decision, sort of the goal of this talk is to take you on a sort of journey across some fields in AI in general, mostly computer vision, and see how self-supervised learning is doing in these domains. So first domain, vision encoding. It's sort of the thing that I'm most familiar with. So we'll talk a bit longer about this one. If we look at the current top quote unquote vision encoders, there's this family of pure SSL-based methods. So Dino V2, V3, Franca, WebDino, AIM from Apple, MAE type of models. And there should be something appearing, doesn't really appear. And the other part of the family is the CLIP and 𝐒𝐸𝐿IP models. And sort of as a side note, maybe for the younger people here, I wanted to add a sketch of the intellectual lineage of CLIP, which is by no means complete, but I thought I'd start like how people came up with the CLIP laws and like, yeah, what kind of works are included in there. So there was an early work in 2015 where you basically treated each image as a distinct class. So you had a data set of, let's say, 50,000 images, which meant you had a last linear layer with a softmax with 50,000 classes. And then you applied different augmentations, but every time the class index is just your image ID, basically your image number. And of course, not particularly scalable with a softmax and a fully connected layer, but it was a learning signal. It's completely self-supervised, of course, and it sort of worked. Then in 2018, Stellar's group developed this non-parametric softmax for contrastive loss, and the contrastive loss has been around by Hatzel et al. And so this was now a self-supervised loss where you can discriminate between thousands of images without your parameter count being dependent on that. So this was achieved by just doing dot products, essentially, and comparing pairwise distances. All right, so this was pretty good. Of course, cross-modal learning has been around for a long time. One of these works, for example, with a margin contrastive work was also from VGG, where they used audio and visual data for cross-modal lip syncing. We ourselves combined these two for cross-modal noise contrastive loss back in the day as well, which worked pretty well. At the same time, there's been around these paradigms of learning from captions, which aren't like particularly human annotated. So this idea of using weak supervised data has been around. And of course, this has been even used, even combined, for example, image text, noise contrastive learning with the convert paper, for example. This was sort of in a particular domain of medical images. And this is pretty much it, right? Like you combine all of these two and then you scale it. And that's sort of the important point. But then you exactly arrive at CLIP, the model, and the learning framework. Yeah, so in terms of idea recombination, you can see, and I sort of highlighted the pure SSL works here in pink. You can see that a big part of it comes from pure SSL. That doesn't mean CLIP, SIGLIP, etc. Perception encoder are self-supervised learns. I wouldn't call them that. I would call them probably weakly supervised, or something like that. Or yeah. But still, the ideas from exemplar CNN, etc., are sort of in there, and the methodology in spirit comes from SSL. So of course the question would be, okay, I mean, these work pretty well, right? And no one has, or not many people have bothered trying to improve SIGLIP, SIGLIP2, or Dino. So is there no more research in SSL for computer vision needed? And for that, I want to tell you this sort of story, which we already talked about in 2020, which is just this task of image clustering, which is, of course, the foundation of the Dino v2 laws. So if you have a couple of images, have a brief think about how you would cluster these images in two clusters. So one thing would be, for example, if you cluster them between red and blue, right? Might be fairly obvious, but actually there's many ways, right? You can also cluster by SUV versus sedan, or you can even cluster whether there's a human also in the images. In this, I would call the ambiguity problem. There might be a better word for it, but there's no correct way to cluster, just like there's no correct way to label, right? It's always context dependent. It depends on what you want to do. And of course, Dino, recall, is a clustering method. So therefore, like which clustering should it take? What's useful? It's completely arbitrary. So what we go back to, apart from like adding a few other things in our paper Franca, which we put on archive last year, is we first of all add a couple of heads. We add multiple heads such that the model can cluster into all kinds of ways to cluster. And in particular, we give each clustering head a different granularity. So, and we do this in a Matryoshka-like way. So what is Matryoshka-like way? If we look at the embedding which comes out of the vision transformer, we use the first couple of dimensions. So this is d by 16. So from the first dimension until d by 16, those we use to cluster the data set into just a few clusters. So this is a very coarse clustering. And then we use the next couple of features, including the ones that we've already used, to cluster the data set into even more detail, so more clusters, into C by 8 clusters. And then eventually we use a full feature vector to cluster the data set into lots of clusters. So this one should be the most fine-grained clustering head. And each head has a different set of parameters, but overall the representation you get at the end of the model has this nested structure. And this nested structure, of course, also means that we save quite a lot of parameters. Yeah, and we have, at least, of course, this doesn't solve in any way this ambiguity problem, but we at least allow the model to dedicate different kinds of ways to cluster in the model and find what works for the model, essentially. And if we look at our ablations, for example, so baseline is just pure Dino v2 in a way model. This is ablation on ImageNet 21K. Cyclic mask is just another augmentation, so this adds a tiny bit, as you would expect from an augmentation. And then if we add this Matryoshka thing, it actually gives a huge gain in dense understanding, which is this in-context evaluation from the Hummingbird paper from DeepMind, but also like a decent gain for linear probing, which is sort of the standard way of measuring representation learning performance. And then, yeah, strong improvement from Matryoshka clustering. And then another thing that we wanted to do here is, of course, Dino v2 and CLIP and SIGLIP are all great, but they're pretty bad in terms of openness. Like the only thing that's open about them is the model weights. You cannot reproduce it. You cannot really understand what went into it. You cannot look at the data. And so there's only a few works which actually do this, like OpenClip and Franca. And yeah, so Franca is our work, where we use a subset of Lion data. So it's completely or re-Lion, I should say. So it's been cleaned for not safe for work and other bad images. And yeah, it's completely reproducible, which is nice and important for us academics. Right. And then another thing we thought about while trying to make sort of the next best vision encoder was that if we look at the features that come out of our vision encoder, we want them to encode semantics and not, for example, the position of a pixel, right? Because the position of a pixel, you get that at the very first layer of the VIT with your positional encodings, or worst case, you can just add it at the end again. So in theory, we want the vision encoder really to be only about semantics. So we thought about just testing this in current vision encoders. And so what we did is the following. We took an image, pushed it through the encoder, and then you get your CLS token out and all the visual features that come out of the patches. And we do this for another image as well. And then we clustered all of those spatial patches. So we ignore the CLS token for now. And then what we get is sort of, for example, for cluster 1, this will contain, for example, for image number 31, it will contain the patch that's located at row location 12 and column location 1. We can rewrite this just instead of 2D patch locations, let's just write 1D patch locations. So cluster 1 contains from image 193, it contains this patch and this patch and so on. And what we can then do is we can then compute the entropy per cluster. So this now measures, like, if we look at all the patches which ended up in cluster 1, how spread out are they in terms of location, right? So if this has a low entropy, this means this cluster mostly appears in one location in the image, right? And remember, the clusters we formed from like the features we got out of the vision encoder. So this tells us if we look at all the entropies of the clusters and we find entropies which are particularly low, it means this cluster only ever appears at one type of location. I hope this wasn't too fast. Otherwise, let me know if you have questions. And of course, a high entropy would mean it, or like the highest entropy would mean the cluster appears in every location equal amounts of times, which maybe you also do not want in theory. But at least for things like, I don't know, a cluster which encodes the sky or a dog ear or whatever, you kind of expect it to be at least spread around. It shouldn't always just appear in the bottom right corner or something like that. And now we can plot two kinds of histogram. I mean, first of all, there's the histogram of these entropies for the clusters for DynoV2 and also for Franca. And for example, if we look at DynoV2, some clusters with near zero entropy are visualized on the left. And you can see that no matter what kind of image you give, so there's an image with an airplane, with someone in a box, and like a street scene, it doesn't matter. Like this cluster always just activates for the same patch location. And so this, and same for the other cluster, these clusters just encode position information as what we're seeing. And Franca actually, mainly due to the Matryoshka thing, actually has on average a quite higher entropy in terms of the clusters we get. But yeah, here we're also using different training data as well, so that also matters. But one question that we had is like, okay, given that we have so many pre-trained models, and Franca, the model we've trained with the Matryoshka, will only stay state of the art for a short while. Can we sort of develop a post-training method to suppress this information? Because this information is really not necessary, and very likely, if we suppress this, it should help. And so that's what we did here.
Yuki, can I ask something?
Yeah.
I mean, it might be because I work on point tracking, etc. And like this position information might be important for tracking tasks, right? Like as long as you have clusters which focus on semantics, why do we want to suppress the ones which also encode position?
Oh, because you can just add them back at the end, right? Because position, like you always know which patch came from where. And so if you have any application which needs position afterwards, you can just add it afterwards.
But might there be correlations between position and semantics that are relevant to tasks?
The mixture of information between position and information.
Yeah, like jointly coding position and semantics might be important for tracking, right?
Yeah. Yes. The question, yeah, I mean, it could very well be that like this is desirable in some settings. I'm sort of the settings we're thinking about, like semantic segmentation. You kind of want a cow also to be detected, even if it is in the sky, let's say, right? Like you don't want this to be cheating in a way via positional information. And maybe another way is also like you don't want it to be what we're doing here with the clustering, right? It means that a dominant feature is actually the position. Like if it's, and clustering is linear, so it means like you can linearly read out the position. So it's really a dominant thing in these features. And so my hunch would be it shouldn't. And maybe the better way would be for, we haven't tested this, but maybe the better way would be, for example, rope-based methods, which
I see.
encode the positional information in a more subtle way.
Okay,
But yeah,
thanks.
I mean, that is true. We didn't actually test that. So eventually, this method I'm going to present will remove this sort of information, but we didn't test it, for example, if it then could be used for tracking applications or something like that. That would be quite interesting.
Mhm.
Um,
So, Yuki, can I
yeah.
also comment on this ambiguity problem you mentioned?
Mhm.
So, in my PhD thesis, I worked on shape clustering. So, I had the same impression. So, basically, this is like a chicken and egg problem, right? The clustering depends on how similar these features are so that you can combine them together. But it depends on how you define the similarity function to get this information. So from what you described about showing these different types of car, different colors, etc., it seems to me that like in this Matryoshka clustering approach, you are basically just performing some hierarchical clustering, right? But in that example, basically the number of clusters remain the same depending on how you define the similarity. So I just wanted to take your opinion. Uh, of course, nowadays we all use the transformer architecture. And actually, the sole purpose of this multi-head attention is to first generate different views of the features and then compute the similarity based on that. So instead of this changing the number of clusters, maybe a better idea could be, of course, I don't know how well this could work, but maybe different heads specializing to different features from different attention heads. What do you think? Would that make sense?
Yeah, I think that does make sense. And I mean, this idea of clustering with multiple heads by itself is not new. I mean, we've done it ages ago as well. Um, and that works. And whether one could do this with like different heads, etc. The only thing that we've discovered sort of is that if you don't have this matryoshka, then the parameters count does blow up because these projectors are fairly large. And for example, Dino's vocabulary or like Dino clusters into like 256K clusters, which is quite a lot. And so actually having these matryoshka heads allows you to have basically hierarchical or multi-headed clustering relatively cheaply.
Nice.
But otherwise, I'm pretty sure there would be many ways to do it. And like I think I saw work back in the day even where you also have a clustering based on like earlier layers of the model. So you would expect those to encode like lower level features and then yeah. So all of these tend to make sense in my opinion. It, but it's also the case that you might not want to over design things. Like I, I also like at some point thought about like, okay, there could be one head which just uses, for example, grayscale images. So that one obviously couldn't cluster based on color, for example. So it would be focused on shape.
Just to correct, so by head, I mean different attention heads
Yeah,
that basically generate different representations of the same thing, right?
yeah,
So maybe one could, for example, capture the color information
yeah,
more, the other more shape, maybe.
yeah. Yeah, but whether it's an attention head or like a MLP projection head, I mean, they
Yeah,
would
yeah,
be
I'm
very.
referring to the projections in
Yeah,
the,
yeah. And these
the attention
projections tend to be
computations.
like multi-layer MLPs,
Yeah, yeah,
but
exactly.
they could be
Because
transformer.
I think the central problem is how we can come up with different representations of the
Yep.
entities, right? That's
Yeah.
the more ambiguous part.
Yeah, yeah. One could try to decorrelate the heads and things like that. But what ends up being often the case, at least from my experience, is like once you add too much regularization, then the model yeah, doesn't work that well anymore. So there's sort of this weird fine balance where you need to give the model freedom, but you might want to hint it in some good direction. Yeah. But yeah, I mean, yeah, I
Thank you.
think there's plenty of things to do here. Yeah. Yeah. So removing this patch positional information from a pre-trained model can be done. So of course, like if you wanted to fully fine-tune the model, that would be easy. You just add a linear layer to predict the position and backprop through the encoder and with a reverse loss, basically, right? Like you flip the sign and try to let the model not be able to predict the position really well. But we want to keep the model frozen. So what we do is we do train a linear layer to predict each patch's position here. And we just have a linear layer which has at the end two outputs. So one is the X position, one is the Y position. And we just predict it with predicting the position ID normalized between 0 and 1. And yeah, then with MSE, we backprop through it and then have a linear layer which basically extracts all of this positional information. And then we take a look at this linear layer. And linear layer has two outputs. So one can see it as us having one vector, which is a row predictor, and one vector, which is a column predictor. So in terms of where the patch is, in terms of row and column. And so what we can now do is we can project any vector into this plane, which we call the positional plane, which is spanned by this row predictor and column predictor. And then what we can do is we can simply apply Gram-Schmidt, which is to project it, and then subtract this contribution from the original vector. So that means we first take our vector z, here zi0, then we project it into this positional plane. So this means this is the vector positional contributions. So all the positional contributions are here. And then we simply subtract it. And then, so we get a vector which is orthogonal to this plane. So in theory, this vector now does not have any component in this positional plane. So in theory, this has all the positional information removed. But of course, you can think like, why should like positional information be only included like very clearly? It could be encoded across multiple neurons. And so what we need to do is we need to do this multiple times. So we can keep this layer once, and then we train a linear layer again. And we keep repeating this, and this is sort of the RASA method that we've developed, the removal of absolute spatial attributes. So we add a linear layer to predict position, and we do Gram-Schmidt to remove the learned positional plane. And we keep repeating this. And after repeating this, it always looks like the following. Each removal of positional information is a linear transformation where you have this identity matrix minus the positional plane. And we can also write it out like the following. So it's this outer product between these projection vectors. And of course, linear transformations, we can just simply keep combining them. So in the end, all of this can be just put into a single linear layer. And of course, a linear layer, again, can be just absorbed into the VIT. So in the end, we can keep the normal VIT architecture and weights, but we've removed all the positional information. So yeah, now on the effect of RASA. So of course, it has an effect on the patch entropy, as we would expect it. So it increases entropy across all kinds of models. So we have less clusters that only encode spatial position. And on downstream tasks, it even improves. And indeed, the improvement is especially for dense tasks. So for example, this in-context semantic segmentation task, but also even for linear probing. And I mean, it's a fairly lightweight procedure. It also doesn't take more than, I don't know, one GPU hour, like 2 or something, because it's just training these linear layers. It's pretty quick. But yeah, there's some quite decent gains for the dense tasks. And then we can also finally take a look at the final model in terms of PCA visualizations for images, comparing, for example, our Franca with other pre-trained models. One thing that's quite clear here from even Dino v3, which is of course very nice features, even Dino v3, you can clearly see this sort of color gradient, which is based on position here, which is not based on semantics. Radio, of course, is very semantic, like it's almost like a semantic segmentation. That's because in the distillation of the radio model, they used a semantic segmentation backbone as well. Dino v2 has all of these artifacts. Dino v2 with registers doesn't have these artifacts, but also has like fairly like position-based encodings. And yeah, same for the other models. Maybe the bottom image is kind of worth looking at, where Franca sort of even differentiates between bicycles and the riders, which is kind of nice. While like, yeah, Dino v3, for example, puts all the riders in inclusive their bicycles into the same feature space. And we even select these images actually properly randomly here. And I mean, these are just PCA visualizations. You don't use PCA visualizations in any proper applications, but it's still kind of nice to see this confirmed here. Oh yeah, and then of course, like sort of what all of these models have a problem with SIGLIP versus CLIP versus Dino v2, they all use different data, right? And so what we need, like if we want to say this is a better pre-training method, we need an apples to apples comparison. So we did this on ImageNet 21K, so this is definitely big enough to mimic larger scale pre-training runs. And everything is sort of fair and equal here. And we see that Franca, the method, outperforms Dino v2 on an equal basis for VITB-based models. And we have some more evaluations for like 3D understanding, which is featured to Gaussian splatting evaluation here, which actually works pretty well. And this in-context learning, which is this dense task, which I've mentioned. So yeah, this work has like a few rather like slightly orthogonal contributions. So we have this new pre-training method, which improves the clustering based on Matryoshka and made sure that everything is sort of open source. And then we have this new post-training method, which actually you can apply to Dino v3 or any sort of other method even. And yeah, this work has been led by Shashank and Valentinos and was a collaboration with Valio AI, which was pretty fun. All right, and so yeah, going to the research question. So this is a nope number one. SSL in computer vision is not that. In case you remember the question, methodological improvements are still abundant. And I mean, I could just mention a few more ideas that could end up as papers. So yeah, there's really a bunch of stuff to do. Moving on to problem number two. So Dino v2 paper has this very, very cool visualization, right? Where you say, oh, if you look at the nearest neighbors in feature space, it really can match something as like distinct as these images. But then often you do this actually on a real data set and you look at, oh, where's the nearest neighbor of this patch, for example, in the whole data set. And you get things like this. Oh, the nearest patch of this ear of this girl, you ask Dino, and then it returns you, for example, this feature from the floor or this other random feature in the background of a group image. And the spoiler is like the method I'm going to show you actually does what you would expect. It returns you like other features or other patch features from ears. And so in this paper, what we look at is this idea of patch nearest neighbor consistency, which is quite intuitive to us. So for example, if I would ask any humans or which features you would expect to be closest, or which pixels would you think would be closest to those of this right shoulder of this BMX rider, they would probably answer with, oh yeah, probably other patches of right shoulders. Maybe then the next closest thing should be patches of left shoulders, and then probably all the rest, like maybe first other human parts, but then like doesn't really matter. Like this is really easy for us humans. And so the question is, how can we put this into an SSL loss? That's what we were thinking about. And so we start off with the standard framework of like a student encoder and a teacher encoder. They get updated, which gets updated by the exponential moving average. And then we have two crops, and we align these two crops such that they actually depict the same part of the image. And we simply do this with a ROI align. So now we have sort of two sets of features which encode the same part of the image and which are equally sized, which is very, very useful. And then we do the same for images in the batch. And now what we're going to do is for all the features in the reference here, which are just a couple of patches from the batch, we're going to compute the similarities at the dense level. So for every feature in our current image, we're going to see how far off is it to all of these reference patches. And then actually we're going to take a distance metric instead of the similarity, so just 1 minus the dot product. And next, what we're going to do is like we're now going to sort these distances. So if you're the patch, let's say at the top left, we've computed the distances to all the patches in the image as well as in the batch. And now we're going to sort them. And this gives you a ranking. And of course, remember that across both views, top and bottom, we are sort of encoding the same parts of the image. So now what we want to say is, okay, we want these sortings to be consistent. And why do we want the sorting to be consistent? If you actually set those distances should be the same, well, then eventually it will just turn to 0. And then you have the same distances. All the features are 0. That's quite useless. So it will collapse. So in SSL, you always need these anti-collapse terms. And this differentiable sorting is also kind of really interesting domain as well, because each per patch permutation is 49 by 49. So the output from the ROI line is 7 by 7. And so the total number of element-wise loss contributions for one batch is 7.5 million. So it really is an extremely dense loss because for every patch location, you're getting this sorting signal. And so, yeah, it works really well. And you only need, I think, 20 GPU hours for training the whole method. Yeah, and we're going to evaluate it with this hummingbird evaluation that I mentioned earlier already. At the high level, it works as follows. You have a training set, and you embed this training data set into feature space and pretend like this is a big k-nearest neighbor database. And at inference time, you retrieve the nearest neighbor in this feature space, and you aggregate the label. And the label in this case is not image level, but patch level. And that's how you do prediction. That's how you do zero-shot, non-fine-tuned semantic segmentation, basically. So it's extremely nice. You don't need any hyperparameter tuning. It's fairly quick and works pretty well. And so on this evaluation on Pascal VOC, we quite well outperform the Dino V2 with registers. So at the same performance, we use 10x less labeled data, for example. And of course, our key comparison here is Dino V2 with registers because that's our starting point. So this, again, is a post-training method. We do not start by training from scratch. Otherwise, it would, of course, take a lot more GPU hours. Here's some of these visualizations of these in context learned semantic segmentation evaluations. And you can see they are pretty nice and crisp. They're actually not the ground truth annotations, as you can see from this image here. Like it doesn't always work perfectly, but it works really, really well. And these are just, no fine tuning at all, just retrieving nearest neighbors. So that does work extremely well, which is pretty cool. And of course, this evaluation that I mentioned earlier, we can do this again, take a patch at the bottom of a horse, look for nearest neighbors in, I don't know which data set this is, but and Dino V2 with registers returns you like a part of a car, a part of a bicycle, human, etc. And 𝐒𝐡𝐨 just returns you from one image, it returns you multiple features from a horse. All horses are even leaning left, which makes sort of sense. And then the next best patch is from another image, this patch of a horse, and then this patch of a horse. And same for like a train patch. Dino V2 with registers does something I don't quite understand, but our model sort of returns a couple of patches that are train related. And yeah, even if you don't do the frozen evaluation, but like linear evaluation. So you train a linear layer for semantic segmentation. We get quite big gains on top of Dino v2 with registers. So yeah, this is a really useful loss for post-training very strong models. And also it's not limited to working with Dino v2. You can put this on top of any other pre-trained method. Wherever you see red numbers, it means we don't improve the numbers from the original model, and blue numbers means we improve the model. And so yeah, it does seem to work across pre-trained backbones. We've yet to try it on Dino v3, I mean, but I'm fairly hopeful. And I mean, despite like Dino v3 also introducing a post-training method, which is very similar, they have a gram matrix, so it's also this patch by patch similarity matrix. But they are sort of limited by their gram matrix from an earlier checkpoint. So yeah, it would be interesting to check this actually. All right, so yeah, that's what we end up doing in recent times fairly often. Post-training is a good domain. It's pretty fun. You're sort of dependent, of course, on the big models. That's why we also started training big models when we have the GPU compute. But yeah. All right, and then just as a sort of very high-level overview, so this was the work we presented last year at 𝐒𝐤𝐥 25. We also have two works which we presented at ICCVs, where we basically do this for video data. And actually, in one of these works, we also use point tracking. And what we're essentially doing is we're saying like features that belong together according to a point tracker, they should have similar cluster distributions. So this makes the loss, also stops the loss from collapsing. And with point tracker, actually the benefit is that we can not apply a loss if the object is not in the image, which in our 23 work, we were just using the Dino v2 model itself to do the tracking. And now with a point tracker, this was even more precise and worked pretty well. So all three of these are post-training works. And yeah, so post-training research is only really starting. All right, cool. I would maybe actually go to another work just because of the time.
We have time, okay.
Yeah, let me continue from here maybe.
These dinos.
Dinos, yeah, dinos. Oh no, not beginning, start. It's my view. Oh, let me. I feel very old. Okay. All right. So vision encoders, we have them here. And then I said I'm going to give an overview about SSL and AI, right? And of course, LLMs is sort of the stereotypical example where you take data, mask it at the right site, and learn to predict the next token. That's sort of the SSL loss, which is very nice and easy. And data can be from web, humans, LLMs, RL, etc. And so SSL, I would say, is the core training principle, even if sometimes the data doesn't come purely as data, but comes from humans. So LLMs, yeah, definitely the biggest idea here behind it is not training in a supervised manner, etc., but with a self-supervised loss. All right, and next, another quick one here is the VLA spatial AI geometry models. So if we look at OpenVLA or Pi 0, 0.5, 0.6, all of them use Dino cyclip backbones, VGGT, of course, and Pi 3 and depth anything use Dino v2, v3 backbones. So spatial and geometry also like sort of covered here. Okay, and now we go to like a more slower topic, which is that, okay, we had this assumption that we always have lots of raw data, right? That's in a way always the selling point of why SSL should work and works, and why it's worth investigating this, because once we have a good method, we can move to all the exabytes of raw data. But then comes along 3D, and then like if we look at the state-of-the-art 3D representation learning paper, actually they use just 15K real scenes, and like me not having worked in 3D, I was a bit shocked that there's an area in deep learning that still works with like such a low number of data samples. Of course, in terms of point clouds, it's still quite commendable and like a huge number of points in all of these scenes, but still 15K real scenes seems so little. So yeah, actually it seems like, at least not out in the open, we don't have abundant 3D data. So one problem we wanted to address is how can we scale 3D actually without having 3D scans? And so our proposed solution is the following. So we take web scale ego videos, basically unsupervised data, and then we apply these geometry models that I hinted at earlier. So this is VGGT, this is Pi3, etc. And we generate video-generated point cloud data, or VGPC for short. And then VGPC, we can create as much as you like, right? Because there's as many videos on the web as you can imagine. So then we can train on this. Of course, now what we need to do is we need to be slightly more careful, because now the data is a bit more noisy. It's not coming from a ground truth 3D scanner. So we need to develop a new SSL pre-training method. And this is what we did in our preprint for archive last year. So first of all, the VGPC pipeline, we download a bunch of videos from the web. We cut them into distinct rooms. We're using a model which detects scene changes here, Pi scene detect or something. And then for each clip, we put it into Pi3. And then we have Pi3 doesn't give you anything for scale and z-axis. So we have some adjustment going on there. And then we have these video generated point clouds, which is now the raw data which we can use for a self-supervised 3D learning method, where the goal is to learn a point transformer V3 architecture. And so these point clouds themselves, they look fairly realistic. They don't look all that much worse compared to, for example, ScanNet data. But of course, the key thing is here that these rooms have never been walked through with an iPad, right? Like no one has ever scanned these rooms. These scans don't exist, and they will never exist. But of course, with these strong BGT-like models, we can actually do something and use these for 3D learning now. And the noise-aware loss that we propose, again, it's a clustering-based loss with optimal transport. That's again coming from here. We have a BYOL-like stabilization loss between the model and the EMA encoder, and then we have a sort of this loss, which we call Laplacian loss, which adds a loss on the KNN neighbor graph on the real world location. So this now takes the XYZ coordinates of a point and says, okay, if the points are not that far from each other, then their features should not be that far from each other. And so this takes a bit into account that sometimes with these reconstruction methods, you have some features sort of floating above the surfaces, etc. So it roughly looks like this. So if we have a noisy point here in gray, then this one simply doesn't get attracted as much to the rest in terms of clustering loss. And so here now I'm showing you some performances. So for example, full fine-tuning on 10% of ScanNet in terms of semantic segmentation, or full fine-tuning in S3 DIS instance segmentation. And we put a bunch of state-of-the-art methods here. So MSC, PPT, and Sonata. Here, Sonata with different sizes as well of pre-training data. And then our method is called LAMEC, which we're going to put here. And LAMEC doesn't use any real 3D samples for training, so ends up at this performance level. But then we can keep using more, right? We can scale VGPC relatively cheaply. We cannot collect more ScanNet data, but we can just scale VGPC. And this works extremely well. And we can actually achieve better performance than Sonata, which uses all of the real data that they could find. At least for S3 DIS, we outperform it. And for ScanNet, we get decent performance as well. Yeah, so here VGPC is sort of, we wanted to propose it as a viable alternative to real 3D scans, and it combines SSL and, for now, weakly supervised scalable data generation. But the progress is so fast. I don't know if you've heard or saw, but there's works basically that are like VGGT, but are completely self-supervised. And these actually work fairly well as well. So we're just testing them out now, but we're thinking we can actually make this whole pipeline completely self-supervised. And so that means videos in, 3D understanding out, which is pretty cool. Yeah, so SSL plus scalable data pipelines enable new frontier for 3D is a hope. So yeah, now we've added 3D point clouds here, very specific. And then, oh yeah, actually, yeah, we do have time, but that was not on. We're gonna move to another problem, which is cross-modal consistency in multimodal large language models. So for example, if we ask GPT 5.2, a question as text, for example, who said jurisprudence is in the eye of the law? And sort of multiple choice question, I think we took it from MMLU. It will reply with, okay, here, none of the above. Okay, fair enough. Maybe that's correct. Probably not, but okay. And then if we paste it as an image of the text, we get actually a different reply, C pound. And of course, 5.2 instant, we don't know all the details, but 5.2 is a fairly state-of-the-art model. So this is a problem, right? Like this is a problem, for example, if you're not typing but showing notes instead, you can imagine like you want your multimodal LLM to be answering in a consistent manner no matter how you present the data. And so what we do is we take this idea of sort of augmentation invariance from SSL, and we simply do a render augmentation invariance check. So we take a few data sets and we present them in all kinds of ways with different fonts, different colors, and different DPI settings. And so how, like the resolution essentially of these, and present it to these multimodal LLMs. And one fun thing we find is, for example, that colored text consistently works better for all of these models. So if you want, for example, the models to be answering correctly, definitely use red font or yellow font compared to black font. That seems to be quite helpful, funnily enough. And then we also experiment with the following, where we present only the text, or we present it as a mixed modality. For example, we present part of the, in this case, system of equations as an image, and then the last question as a text into the LLM. Or we present the whole thing as an image. In this case, yeah, the last equation is also included in the image, basically. So we call this text, mixed, and image only. And then we show like, okay, which questions get answered by all three modalities correctly. In this case, we're talking about DeepSeek VL small, and this is around 40%. And then if the model, we're going to look at if the model could choose which modality to answer, then it could achieve, for example, all the way 80%. So it could double the performance if it could only choose which modality to answer the question from. So if it always has to use all three, or like if it has to be consistent, then 40%. If you combine image and text, and you get the plus 10%, and yeah, so it leaves a lot of performance on the table essentially. So yeah, if the model knew which modality to choose, it would get huge performance gains. And now the question is like, when is the model actually consistent? This would be quite useful to know. And so what we take is we sort of do like a diagnostic check where we either we take a couple of ImageNet categories and we make an image, which we call written down. So this is an image with the text goldfish written on it. And we, of course, take the word goldfish. And we put all of these into the multimodal LLM separately, one after another. And we compute the cosine similarity of these. How similar are these? And this is plotted on the x-axis. So if they are completely give you the same vector, that would be 1. Yeah, if they're orthogonal, then it would be 0. And the render equivalence rate now is just this performance that we had earlier. So how consistently does a model answer when you presented one or the other modality? we find that actually this very simple, stupid check of seeing whether ImageNet categories, if you write them down or if you embed them as a text, if that correlates or if that gives you similar features, that actually is quite indicative of how render equivalent the model is, which we found quite surprising, that something seemingly complex, at least complex how it evolved during the pre-training, can be checked with something as simple as cosine similarity here. And yeah, so here we use this augmentations, quote unquote, for analysis instead of training. And we find MLLMs are inconsistent between image and text. So yeah, I think this isn't quite an SSL work. It's completely MLLMs, a bit of interpretability perhaps. But SSL does yield ideas here and tools for annotation-free analysis. And so put differently, if you're sort of at this point, what you can do is sort of just do both. And that seems to work here. All right, and then, all right, multimodal LLMs. I think I have a fairly short part here. I did a bit of research of what's happening here. So if we look at the Gemma models, that's 𝐒𝐤𝐿, QUVA, 𝐒𝐤𝐿, Cambrian 1 uses DynoV2 and CLIP, GLM uses AIM-V2, and yeah, InternVL, CLIP-like, Qwen, 𝐒𝐤𝐿, SeedVL, MAE with CLIP, Molmo, MetaClip, and probably GPT-5 and Gemini, something along those lines, one could imagine. And so yeah, MLLMs are also sort of part of this this tribe. So yeah, I sped up a bit, but I think that's fine. We'll have more questions, I think, to discuss. The question whether SSL is dead. I don't think it's dead. I think it lives on. And actually, from this image, it took me ages to generate it because the generative models are not that good. It looks like it's a decision between left and right, but actually the paths do merge and just seems to become a common technology that now everyone uses one way or another. And yeah, so in terms of conclusion, methodology, first of all, is not done. It's effective in related domains. So if you apply it for text, image, etc. Importantly, and I think this is especially interesting for academia, is like thinking about scalable data pipelines that actually, I mean, if there's one thing we now know really well, is that it's all about data. It's not about all that much about thinking smart and adding all sorts of regularizations. Instead, like really think about data. At least that's sort of what we're learning from the LLM space. And then, yeah, SSL can be used also for analysis and interpretability. Yeah, I hope I wasn't too quick now. Also, I have postdoc positions, so do let me know if there's anyone interested. The one work, by the way, that I skipped because also like it's a bit more like doesn't quite fit well, but you can also use SSL for pruning pre-trained models. Is basically the message of that work that I skipped, and it works quite well. It's a pretty heuristic method. We use an evolutionary algo, etc. But yeah, so I think I'm happy to take some questions.
Thanks a lot, Yuki, for this great talk. Some people had to leave because of meetings and so on, but we can stop the recording at this point for discussion.